Atoms achieve lower energy or a stable state when they form bonds in a chemical reaction. And using the Pauling scale, so we can classify the different types of bonds based on a difference in electronegativity. So ionic bonds involve a transfer of electrons. So for example, with sodium chloride, so you end up with an ionic bond between the sodium cations and the chlorine anions. So the difference in electronegativity of these elements is greater than 2. Now covalent bonds, on the other hand, involve sharing of electrons, and these can be polar, where the difference in electronegativity is between 0.5 and 2. So the electrons in this bond spend more time around the oxygen. Now non-polar covalent bonds occur between atoms with a similar electronegativity, with a difference less than 0.5, and the electrons in that bond are equally shared. Now metallic bonds involve electrons that are free to move around. So for example, if you have a metal lithium bar, you get the lithium atoms being ionized, and the valence electrons are free to move around. As we saw, polar covalent bonds involve electrons in the bond being unequally shared between the atoms, because the atoms have a difference in electronegativity between 0.5 and 2. And where this difference is greater than 1.7, the bonds have ionic character. So because the electrons in the bond are not equally shared, they spend more time around the oxygen, in this case, and create a region of negative charge, and leave a region of positive charge around the hydrogen. Now a dipole moment is a vector drawn from a negative to a positive charge, and it has the magnitude of the charge by the distance between them. But in chemistry, we draw the dipole moment from the positive dipole to the negative dipole, and this signifies that the covalent bond is polar. So polar covalent bonds can also occur between a metal and non-metal, such as beryllium and chlorine in beryllium chloride. So as we can see, the difference in electronegativity is less than 2. So we need to examine the properties of the compound and the electronegativity together to determine if the bond is covalent or ionic. The graph of the potential energy versus the interatomic distance is useful for representing the interactions between atoms. So if we consider these hydrogen atoms and they come closer together, you start getting some attractive forces between the nuclei and the electrons. And as the atoms keep getting closer and closer together, you start getting repulsion between the electrons when their orbitals overlap. And the repulsive force increases rapidly because the nuclei will also repel each other. And then superimposing the attractive and repulsive forces, you obtain this graph of the force. Now from electricity and magnetism, the force is equal to the negative of the slope of the potential energy with respect to the interatomic distance. So therefore at this point, where the attractive force balances the repulsive force, so the net force between the atoms is 0, the potential energy is at a minimum. And this here is called the bond energy, or the energy required to separate the atoms. And this length here is the bond length. Let's look at some of the properties of covalent bonds, using carbon-carbon as an example. So in this ethane molecule, we have a single bond, and we call this a sigma bond. The valence electron orbitals overlap head-on, and out of the 3, it has the longest length and the lowest bond energy, so it's easier to break apart. So this double bond in the ethylene molecule consists of 1 sigma and 1 pi bond, and the electron orbitals overlap side-on in a pi bond, which we'll see later. And it has a length between a single and a triple bond, and its bond energy is between that of a single and triple bond. And here we have a triple carbon-carbon bond in the acetylene molecule, which consists of 1 sigma and 2 pi bonds. And out of the 3, it has the shortest bond length and the highest bond energy. So it's the most difficult to break apart. And note that in these covalent bonds, the bond length is influenced by both the size of the atom's core and the bond order, so single, double or triple. We can understand the strength of the interactions between cations and anions using Coulomb's law. So the Coulomb force in this context is proportional to the positive charge of the cation and the negative charge of the anion, and inversely proportional to the squared distance between them. So for example, if we consider calcium chloride, and if we compare this to sodium chloride, then the calcium anion, in this case, carries a 2+ charge compared to the sodium cation, so the interaction between the calcium and chlorine ions is stronger than the interaction between the sodium and chlorine ions. And the other governing factor is that the calcium ion has a smaller ionic radius than the sodium ion, so the distance between the centers of these ions is smaller than the distance between the centers of the sodium and chlorine ions. So therefore, the interactions between the calcium and chlorine ions are again going to be stronger in that regard. Ionic solids are formed due to ionic bonds where the metal cations lose electrons to non-metal anions, and this results in strong electrostatic forces. So ionic compounds, such as sodium chloride, form solids at room temperature, and due to the strong electrostatic interactions, and as we saw using Coulomb's law, the strength of the interactions depend on the charge and the ionic radii. So these properties lead to a higher lattice energy. So because the electrons are highly localized, ionic solids tend to be poor conductors. But if you dissolve an ionic solid, such as sodium chloride, into water, then the ions are free to move around and conduct electricity in a liquid state. And later when you explore material science, you'll see different arrangements of ionic solids, where the basic idea is that the cations and anions in an ionic crystal are arranged in a periodic 3D array which maximizes the attractive forces while minimizing the repulsive forces. As we've seen, metals have a lower electronegativity and lose electrons. So for example, magnesium atoms interact. So being in group 2 of the periodic table, the magnesium atoms lose 2 valence electrons, which become delocalized, and we represent this using a sea of electrons model, where the positive metal ions are surrounded by delocalized valence electrons. So the attractions between these cations and electrons are what hold the metal together. And the free surface electrons are responsible for the shininess of the metal, so they reflect light and give metal its luster. And also these metallic bonds with free valence electrons make the metal more ductile, meaning it doesn't fracture suddenly, and malleable, so it's easy to work it in different shapes. And because the electrons are free to move around, metals are good conductors of electricity. The properties of metals can be altered by alloying them together, and basically alloys are formed by melting metals and also non-metals or metalloids and combining them in their liquid state to be able to form a homogeneous solid, as we want the properties of the solid to be uniform. So one type of alloy is an interstitial alloy, and this requires elements with a large difference in atomic radius. And a classic example is steel, which involves alloying iron with carbon. And in this case, carbon is referred to as a metalloid, so it exhibits properties somewhere between a metal and a non-metal. So here, carbon atoms get lodged between the iron atoms in the iron lattice, which are referred to as interstitial sites. And basically, carbon increases the strength of iron through a work hardening effect by distorting the crystal lattice, which will make more sense when you study material science. Another type of alloy is a substitutional alloy, which is formed by combining elements with a comparable atomic radius. And a typical example is brass, which is formed by alloying copper and zinc. So brass consists of around 66% copper and 34% zinc. So in this case, zinc atoms substitute for some of the copper atoms in the copper lattice. Lewis diagrams are used to determine the skeletal structure of a covalently bonded molecule or polyatomic ion using a set of rules. So first we determine the number of valence electrons. So using this example of the sulfur trifluoride cation, sulfur has 6 valence electrons and fluorine has 7. So given there's 3 fluorines, so in total we have 27. Now if we have a cation, we subtract an electron to get that charge, or an anion, we add an electron to get a negative charge. And now we sketch the skeletal geometry with the least electronegative atom in the middle and attach that to the other atoms using single bonds. So in each bond, 2 valence electrons are shared, and now we assign the remaining valence electrons to the outer atoms to get a complete octet, and now we assign the remaining electrons to the central atom to complete its octet. This is our final Lewis dot structure. And we'll keep adding to these rules because there's cases where multiple Lewis diagrams exist to represent a molecule. A molecule can have more than one equivalent Lewis dot structure. So if you follow these rules as we did previously for this nitride ion, you'll obtain the following Lewis dot structure. And I'll leave this part for you as an exercise. Now an additional step is to move 2 valence electrons from an outer atom to form a bond with the central atom. And we repeat this until the central atom has a full octet. So here we can see that nitrogen now has a full octet of 8 electrons. Now we could have done this using the other oxygen. So we call these resonance structures, which are both equally valid Lewis dot structures for this anion. And these bonds are all equivalent. So therefore we can represent the Lewis dot structure as follows by combining those two. So these bonds have the same order So what we do from one of the resonance structures, we have a single bond plus a double bond, and then we divide by the number of bonds. So these bonds have an order somewhere between a single and a double bond. We can come up with more than one Lewis dot structure for a molecule that are not equivalent. So for example, if we follow the following steps that we've done earlier to obtain a Lewis dot structure for beryllium chloride, which I'll leave as an exercise. Now to determine which Lewis dot structure is the most likely correct, we introduce the concept of formal charge, which is equal to the number of valence electrons minus the number of free electrons and minus the number of bonded electrons on 2. We know that chlorine has 7 valence electrons and we have 6 assigned electrons, and then minus 2 electrons per bond divided by 2. So basically the concept of formal charge assumes that those electrons are shared equally between the bonded atoms. And beryllium has 2 valence electrons from the periodic table, minus the free electrons, and then minus the number of bonded electrons on 2. So the goal is to get a formal charge of 0 for the central atom. So this is the likely correct Lewis dot structure. Let's draw the Lewis diagram for boron trifluoride. So we first determine the number of valence electrons, so 3 for boron and 7 for each fluorine. So that gives a total of 24 valence electrons. And now we draw the skeletal geometry of the molecule with the least electronegative atom in the middle. So each bond takes up 2 electrons. And now we complete the octet of the terminal atoms, and now we're left with 0 valence electrons. So therefore we can skip step 5, because there's no more electrons to add to the central atom. Now calculating the formal charge of the fluorine, where the electrons in each bond are assumed to be shared equally between the atoms. So fluorine has 7 valence electrons, minus the free electrons, minus the number of bonded electrons on 2. So each fluorine has a formal charge of 0. And boron has 3 valence electrons, minus 0 free electrons, and then minus 6 bonded electrons on 2. So boron also has a formal charge of 0. So given the formal charge on the central atom is 0, this is our likely Lewis dot structure. Let's draw the Lewis diagram for the sulfur trifluoride anion. So again we determine a number of valence electrons using the periodic table, and then we add an electron because we have a negative charge. And now we draw the skeletal geometry according to step 3 with the least electronegative atom in the middle. So in each bond 2 electrons are shared, and then we complete the octet of the terminal atoms. So that leaves us with 4 valence electrons, which we now put on the central atom. And now we'll calculate the formal charge for each atom. So this assumes that the electrons are equally shared between the atoms in each bond. So a quick way we can do this is draw a circle around each atom, and then subtract the assigned electrons from the number of valence electrons. So fluorine is a halogen, so it has 7 valence electrons, and sulfur has 6 valence electrons. And then we subtract the assigned electrons, and here sulfur has an expanded octet of more than 8 electrons. So for elements in period 3, the additional electrons above 8 will fill the d orbitals. Let's draw a Lewis diagram for a free radical. So here we have nitrogen dioxide, and in step 1 we determine the number of valence electrons from the periodic table. And now we draw the skeletal geometry with the least electronegative atom in the middle. So 2 electrons are shared in each bond, and now we complete the octet of the terminal atoms, and we assign that 1 electron to the central atom. And now we calculate the formal charge. So what we do is just subtract the number of assigned electrons from the number of valence electrons. So oxygen has 6 valence electrons, and nitrogen has 5 valence electrons. So what we can do here is take 2 valence electrons from oxygen and use them to assign a bond. And now we'll recalculate the formal charge, and this is one of the 2 resonance structures of nitrogen dioxide. So note that we couldn't assign another bond to nitrogen because nitrogen is in period 2 and it cannot have an expanded octet. Let's draw the Lewis diagram for xenon hexafluoride. So first we determine the valence electrons using the periodic table. So 8 valence electrons for xenon being a noble gas, and 7 valence electrons for fluorine being a halogen. So given we have 6 fluorines, we have a total of 50 valence electrons. And now we draw the skeletal geometry with the least electronegative atom in the middle, being the noble gas, which has a stable outer shell. So 2 electrons are shared in each bond, so we subtract 12 electrons from our valence electrons. And now we complete the octet of the terminal atoms, which leaves us with 2 electrons. And we assign the remaining electrons to the central atom. So now if we determine the formal charge for each atom, which assumes that the electrons are shared equally in each bond, so just draw a circle around each atom, and then subtract the assigned electrons from the valence electrons. So this is our likely Lewis diagram. Let's draw the Lewis diagram for the acetate anion. So first we determine the number of valence electrons, and because we have an anion, we add another electron. And now we draw the skeletal geometry with the least electronegative atom in the middle, except for hydrogen, which is an exception. And this chemical formula tells us that we have 3 hydrogens attached to a carbon and 2 oxygens attached to another carbon. And now we complete the octet of the terminal atoms, where hydrogen can only take 2 electrons in its valence shell. And now we can calculate the formal charge on each atom. So what we can do is take 2 electrons from one of the oxygens to assign a bond between oxygen and carbon. So now you can see that carbon has a formal charge of 0, and the lower oxygen has a formal charge of 0. And therefore this here is our likely Lewis diagram for our acetate anion, where the net formal charge is equal to the charge on the ion. And note that this is a resonance structure, because we could have assigned the bond from the upper oxygen also. The Lewis diagram for the acetate anion is given below. Now to form acetic acid, which atom would a hydrogen atom bond to? Well, if we calculate the formal charge of each atom, which assumes that the electrons in each bond are equally shared, then you just subtract the number of assigned electrons from the valence electron. So that gives a formal charge of 0 for the hydrogens, and carbon has 4 assigned electrons and 4 valence electrons. And similarly for this carbon, and for the upper oxygen, oxygen has 6 valence electrons, minus 6 assigned electrons, and the lower oxygen has 6 valence electrons, minus 7 assigned electrons. So what we do is take 2 electrons from this oxygen and create a bond between the oxygen and the hydrogen to form acetic acid. So therefore this oxygen here now has 6 assigned electrons, and this hydrogen has 1 assigned electron and 1 valence electron, and therefore this is a likely Lewis diagram for acetic acid. Valence shell electron pair repulsion theory uses Coulombic repulsion between the electrons as a basis for predicting the geometry of a molecule, or a polyatomic ion. So consider beryllium hydride as an example. We first draw the Lewis diagram and focus on the central atom, which has 2 valence electrons. Now if this atom is excited, an electron jumps to the 2p orbital, and these bonds between the beryllium and hydrogen are identical. So what we do is combine or hybridize an s and a p orbital to form 2 sp orbitals, which are at the same energy level. So the resulting orbital behaves 50% like an s orbital. So if we draw our orbitals, so each have 1 electron in them, and these overlap with the s orbitals of hydrogen. So to get the maximum repulsion between these electron pairs, the angle between the bonds in this molecule are 180 degrees. So here we say beryllium is sp hybridized, and the geometry of the molecule is linear. Let's determine the molecular geometry of a molecule with 3 sigma bonds and no lone pairs of electrons around the central atom. So first we draw the Lewis diagram and the electron configuration of the central atom in its ground state, and when the atom is excited, an electron jumps to the 2p orbital. And given we have 3 sigma bonds, we hybridize 1s and 2p orbitals to obtain hybrid sp2 orbitals at the same energy level. So that leaves 1p orbital unhybridized. So the resulting sp2 orbital behaves 33% like an s orbital. So if we draw these orbitals around the boron atom using valence shell electron pair repulsion theory, where we maximize the distance between the electron pairs, and these hybrid orbitals overlap with the p orbitals of fluorine. The molecular geometry looks something like this, and maximizing the distance between the electron pairs, the bond angles are 120 degrees. So here boron is sp2 hybridized, and the geometry of the molecule is trigonal planar. Let's determine a molecular geometry for a molecule with 2 sigma bonds and a lone pair of electrons. So first we draw the Lewis diagram and focus on the central atom. So the valence shell of sulfur has the following electron configuration. And in the excited state, an electron jumps from the 3p orbital to the 3d orbital. So because we've got 2 sigma bonds and a lone pair, we hybridize 1s and 2p orbitals, where one orbital holds the lone pair and the other holds separate electrons to form the sigma bonds. And we're left with an unhybridized 3p and 3d orbital to form the pi bonds. So as we've seen, the sp2 hybrid orbital has 1/3 s behavior. So the orbitals in this molecule look something like this, where one of them holds the lone pairs and 2 are used to form sigma bonds with the oxygens. So due to the additional repulsion provided by this lone pair, the angle between these bonds is slightly less than 120 degrees. Sulfur is sp2 hybridized, and the geometry of the molecule is bent. Let's draw the molecular geometry for a polyatomic ion with 4 sigma bonds. So we first draw the Lewis dot structure and focus on the central atom being nitrogen. And when this atom is excited, an electron jumps from a 2s orbital to the 2p orbital. And because we have 4 bonds, we'll hybridize 1s and 3p orbitals to form 4 sp3 hybrid orbitals at the same energy level, each with 1 electron. So the hybrid sp3 orbital has 25% s behavior. So to maximize the distance between the electron pairs in each bond, the geometry of this polyatomic ion is 3-dimensional and tetrahedral, as we can see from this model. And the angles between the bonds are 109.5 degrees, with this one coming out of the screen and this one going into the screen. Let's draw the molecular geometry where the central atom has a lone pair of electrons and 3 sigma bonds. And the electron configuration of the valence shell of sulfur is given below, but since we have a polyatomic ion, we have 1 less electron. And in the excited state, an electron from the 3s orbital jumps into the 3p orbital. And given that we have 3 sigma bonds and 1 lone pair, we'll hybridize 1s orbital and 3p orbitals. Well, 1 orbital takes a lone pair, and 3 orbitals are used to form those sigma bonds. So the resulting orbital behaves 25% like an s orbital. And using VSEPR, where the electron pairs are at the furthest distance due to repulsion, we have the following molecular geometry. And when we construct the molecular geometry, we ignore the lone pairs. So what this looks like is a pyramid where the base has 3 sides. So we call this a trigonal pyramidal molecular geometry, where the sulfur is sp3 hybridized. Let's determine the geometry of a molecule where the central atom has 2 sigma bonds and 2 lone pairs of electrons. So given the electron configuration of oxygen, in the excited state, 1 electron in a 2s orbital jumps to the 2p orbital. And then 1s and 3p orbitals are hybridized to form 4 sp3 hybridized orbitals, where 2 orbitals hold the 2 lone pairs and 2 are used to form the sigma bonds with the hydrogens. So the resulting orbital behaves 25% like an s orbital. And using VSEPR, we maximize the distance between the lone pairs and the bonds due to electron repulsion. So we ignore the lone pairs when we draw the molecular geometry. So this molecule has a bent geometry, where the angle between the bonds is slightly less than 109.5 degrees due to the additional repulsion from those lone pairs. And oxygen is sp3 hybridized. We can determine the geometry of a molecule or polyatomic ion a lot quicker using the steric number, which is equal to the number of sigma bonds plus the number of lone pairs of electrons around the central atom. So for example, for this sulfur trifluoride cation, we have 3 sigma bonds around sulfur plus 1 lone pair, so that gives 4 hybridized orbitals. So therefore we hybridize 1s and 3p orbitals. And given that there's 1 lone pair, the geometry is trigonal planar. Now let's look at the acetylene molecule. So here we have sigma bonds and pi bonds in green. So if we look at each carbon separately, the steric number is 2 sigma bonds plus 0 lone pairs. So therefore we need to hybridize 2 orbitals, and carbon is sp hybridized. And you'll get the same result for the other carbon. And therefore the angles between these bonds is 180 degrees due to VSEPR repulsion. And the geometry of the molecule is linear. And I'll leave it for you to do the other examples and post your answer. Consider the acetylene molecule, and if we calculate the steric number for each carbon, and therefore carbon is sp hybridized, and you'll get the same result for the other carbon. Now if we look at the electron configuration for carbon, when it's excited, an electron jumps and 2 orbitals are hybridized to form the sigma bonds. So for the carbon on the left, we have an sp hybrid orbital and another sp hybrid orbital on the other side. And this overlaps with the orbital of hydrogen, and this one overlaps with the sp hybrid orbital of the other carbon. So here we have sigma bonds where the orbitals overlap head-on or directly. And as we can see for each carbon, there's 2 unhybridized p orbitals. And these are used to form the pi bonds. And the pi bonds overlap to the side, so the pi bonds are formed at a higher energy level than the sigma bonds. And the sigma bonds prevent translation, whereas the pi bonds prevent rotation of the molecule, to make it maintain that linear shape, with bond angles of 180 degrees. Consider the butene molecule, which has the following molecular formula, and we can see that it has 2 structural isomers. So in these isomers, you can see that the atoms are arranged differently, and the double bonds are located between different carbon atoms. So in this case, the pi bonds prevent rotation of the molecule, which leads to these isomers. So we can calculate the steric numbers of each carbon, and in this case they have 0 lone pairs, so the steric number is equal to the number of sigma bonds. So the first two carbons are sp2 hybridized, and given that they have no lone pairs, they have trigonal planar geometry, where the bond angles are around 120 degrees, and the other two carbons are sp3 hybridized, as the steric number is 4. So given that they have no lone pairs, the geometry around those carbons is tetrahedral. And I'll leave it for you to determine the molecular geometry around the carbons in the other isomer. The Lewis diagrams of the isomers for dichloroethane are given below. And we're first asked to show that the Lewis diagrams are valid, so we assume that the bonded electrons are shared equally between the atoms, and hydrogen has one valence electron minus one assigned electron, gives a formal charge of 0. And if you do the same for the carbon, and the same for the chlorine, so the formal charge on all these atoms is 0. And you can do the same for this isomer. Now let's determine the hybridization and molecular geometry around the carbon atoms. Well, around the carbon atoms, we have 4 sigma bonds and 0 lone pairs, and therefore both carbons are sp3 hybridized. The geometry around both of them is tetrahedral, and that's also true for this isomer. And now let's sketch the molecular geometry of the isomers. So around the left carbon, and you have another tetrahedral arrangement around the other carbon as follows. And I'll leave it for you to sketch the molecular geometry of the other isomer. The Lewis diagrams of the isomers of dichloroethane are given below. Identify the types of bonds and sketch the orbital overlap diagrams. So for the left isomer, you can see that there's single bonds all around the carbons. And then calculating the steric number for each carbon, we have 4 sigma bonds minus 0 lone pairs, which is 4, but the carbons are sp3 hybridized. So around the left carbon, we draw the sp3 hybrid orbitals while ignoring the back lobes, and then these each overlap with an s orbital of hydrogen. And on the right hand side we have head-on overlap with the other sp3 hybridized orbital of the other carbon, and an overlap with an s orbital of hydrogen on the top. And on the right hand side there's head-on overlap with a p orbital of chlorine, which is the orbital where chlorine accepts a shared electron. And similarly we have head-on overlap with the p orbital of the other chlorine. And I'll leave it for you to do the same for the other isomer.